but let's just quickly go through the other two cases, the cylindrical coordinates and spherical coordinates. It's basically the same, except that there are some, the argument is a little bit, there's an extra step, a little bit slightly more complicated, but it's basically the same. And the equation you get is a little different. And then it can also depend on situations. The Cartesian coordinate, we starting with Cartesian. Now is the next is cylindrical coordinate or circular cylindrical, because cylinder can be non-circular, but we are usually just refer to circular cylindrical coordinate. It depends on rho, phi, and z, and I suppose you know those coordinate. Right. So the first thing is to write the Laplacian in cylindrical coordinate, and usually just look up a table. I suppose your textbook has whether in front or in the back there's a table for these things. But, or you look back the curvilinear section that should have that form. So the Laplacian is this form. The cylindrical radial coordinate rho, and then there's phi derivative, rho square, and also square psi positive phi square. Phi is the signal for angle, and the z is actually the same as Cartesian coordinate. So one of them should be the same. You should get exactly the same equation for one of them, a square. Right? Again, k squared can be positive, negative, and I mean, later on your textbook has some general form of k that you can still use the separation of variable method, but generally just do a little bit analysis to see whether that the equation accept separable solutions. That should be straightforward. But we just go back to this Helmholtz equation. The solution, separable solution, again, finally you sum over maybe infinitely many of these separable solutions, but one of them is separable in the sense of there's a function p, or the grid letter, capital letter rho is just, and then a function of rho, and then capital phi, that depends on little phi, and then capital Z depends on C. Okay, so that's the form we assume, and the process is the same. Substitute into the equation and divided by the equation itself, right? So put this into here and divided by psi, right? And after you do that, the rho derivative only operate on this capital P, and so there were these two factors in front, but you divide it by the whole thing, so you get 1 over P out here, the first term. So 1 over P. Now the partial derivative becomes a total derivative, and likewise the second terms you get 1/(1/) phi now. Then you have rho square, e square, psi, e phi square. And the third one, just like what we did last time, 1/(e square, c, e c square. And the final one would just be a square constant. Okay, so we get something similar like last time, so especially the third term is exactly the same, so we can set that the constant. So this is a constant, this is a function of z, and this is a function of phi divided by rho square. And this is a function of rho only, right? And the complication is this, the first two terms couple the rho coordinate and the phi coordinate, so you need to do it in 2 steps, right? Because now you cannot just say this is a constant, and that is not a constant, obviously. That's just, but we just do it step by step. The first one is this z term. Like last term, we assume it's just a constant, but this term, I think we assume to be L square. Last time there's a negative sign, but we already said that whether it's positive or negative doesn't matter. We choose whether it's positive or negative according to the problem. Sometimes it's positive, sometimes it's negative. But we just assume it's L square at this stage, and you might as well later choose it to be negative. So L is imaginary times a positive number. Right, so that is fine. And then these two terms add up to be a constant, so L squared plus K squared in here. No, that's one part. So you can write down the general solution now. Z is either you use cos or sinh. The A cos, now x plus E sinh. Z, that's Z. Or exponential function. So either way, you choose 2 independent solutions for this equation. So that's just like what we did last time, except last time we used sine and cosine and exponential I. Right? And so that doesn't matter. You can interchange this or the previous one. It's just treating whether there's an I in L. Right. And now once we did that, the next step is to resolve the coupling between these two terms. And the one thing is what we can do, multiply rho square throughout the whole equation, right? Yeah, did I miss a row? Yeah, miss a row here. The row P, row, yeah. Okay, so multiply rho square, and so the equation becomes rho P, P rho, P rho. It's 1/(phi) e square psi. I think this is not psi. This is phi capital phi e phi square. Right, and the last two terms is L square plus K square times rho square. Right, this is a constant L square. This is K square. L square plus K square, and then multiplied by rho square. Okay, so that's we did one more step. Now you argue that this is a function of rho. This is a function of rho. This is a function of phi. So these two add up to be a constant, and this is also a constant. So you might as well just define a name for this term, and now this term is chosen to be minus m squared. Okay, with that, this is like the equation in here, just exactly the same except the negative sign. So go back to last term, so you can have either sine m phi cosine m phi, or e to the plus or minus I m phi, right? But then m doesn't necessarily have to be an integer, except if the problem involves all the value of phi, or the azimuthal angle. So if the problem doesn't involve all the azimuthal angle, that can be any real number, just like any Cartesian coordinate would it. So whatever the shape, or it might be depends on the boundary condition. So if you have a problem that involves in all 2 pi value of phi, then the form of the equation, the solution is the same. It's just whether m is an integer or not, right? So so you can either write a cosine m phi, e sine m phi, and then for either a either I m phi. Right. The form of the solution is just the solution of the simple harmonic oscillator equation, so that doesn't change. The only thing change if the problem has no boundary in the phi direction, to involve all azimuthal angle 0 to 2 pi, then basically impose the periodic boundary condition on the function phi, meaning that you rotate phi adding 2 pi, you get the same value. So that will impose the condition on m. For the first one, m will be integer, positive, or maybe 0. If you have 0, obviously this term will be 0, but this term will be just a constant, which is also acceptable. So it can be 0, 1, 2. And likewise, the second one is also fine. You can use m as 0, 1, 2, just like what we did with Fourier series. But in that particular case, when you involve all azimuthal angle, you can just write like just a single term, right? Just write like a. Instead of that, using m as positive integer, you can write this a on m, just I m phi. The m is all integer, right? That is also fine, right? Maybe m is from 0 to plus or minus 1, plus or minus 2. So that is, you can just use one single term to represent all 2 independent solutions, because plus and minus is independent of each other. Okay, and so that's the phi solution. But however, if your problem has a boundary in phi, it's not total 2 pi, say just half circles, half cylinder, you impose a back boundary, then the condition will be different. It depends on what boundary condition you impose, or maybe not that easy. Maybe it's just separate just a sector or given angle. However, if you impose a boundary, something like that, then you don't have this kind of situation, right? So you just treat it like any boundary condition that. So you may have two separate boundary that you need to impose boundary condition, and that will set the what the m's are. Okay, so that's just. I mean, we usually don't consider these cases, but it could. I mean, in general, we can consider a problem like that. But in the case, in the most likely case we consider would be involving all azimuthal angle, then this would be an integer, m would be an integer. Okay, so finally, we get one equation, because this is just minus m squared, and this is L squared plus k squared. And I think your textbook introduced another a parameter for n. I think this is called Yeah, I get the wrong page. Let's see, it's called n squared. This one is called n squared. It doesn't matter whether you use it just make the writing the solution a little easy. Write n because this n times rho square, so or n times rho square. Right? You can rewrite the equation in the form of what we call the Bessel equation. Just write rho multiply p to the other side. Rho dp rho plus. Now this is n squared, so it becomes n squared rho squared and minus m squared times p equals to 0. Okay, and so that is the Bessel equations. All right, and the solutions are this is this is for p will be you have two equations. It depends on whether this is m is an integer or not. So if m is an integer, then you get the Bessel function of the order m, integer order m, right? So and so there are complications whether that is integer. If it's not an integer, if it's just a real number, then that is simply a Bessel function the m. This is n rho because that takes the value of parameter. Sometimes we write x, but then we normalize that this. And for this particular case, that's easy. You change the variable n times rho as x. Then you get multiply n and divided by n. Basically doing next thing, you just change rho to x, you get exactly the same form of the operator. Just change as x squared. Right? Anyway, this is the solution if m is just a real number, non-integer. Right? The m belongs to integer. Right? But if it is integer, then you can use the what we call the Neumann function that we talked about last time in the ODE chapter. And I think the text use y. Some people use n, but doesn't matter. Integer. Right. Okay, so because m is integer, j sub m and j sub minus m are linearly dependent, so we cannot use the first form. We need to use the second form. Okay, and that would be the general solution. Okay, so the general solution will be psi is just sum over whatever. Now this L may not be a sum, maybe an integral. It depends on problem. So L and M. You have either a cos L G E C L G, and then multiplied by this e to the IM by, and then just use m as an integer if m is an integer. So, then that covers both terms because m now let m goes from minus infinity to infinity in all the integer value, right? And you can absorb the coefficient into the a and b also, and then you have this. In that case, because it's an integer, then you need to use the second situation. Why? Right, that would be, and then you figure out that these things, the coefficient will depend on L and M. L and M. Okay, and now you use the boundary condition to figure out the coefficient. There's some redundancy because but doesn't matter. All right, that's the general form, and it's pretty straightforward. Any question up there? So very, very straightforward. All right. It's like a review for some of you, right? And now the example is very simple. Now becomes a eigenvalue problem. The k squared, instead of calling k squared, call it lambda. Yeah, that doesn't matter. So you can erase this one. Once we figure out all the solution, just erase it. And this way, the problem is just like a cylinder. It's a cylinder. And the radius of the circular cylinder is R, capital R, right? And it's eigenvalue problem with the boundary condition of psi or 0, all surfaces, all the surfaces find 0, right? I think so. And then k squared become lambda. It doesn't really matter. And now the solution, you can just plug in this solution and figure out what all the terms. Now with the top and bottom boundary are both 0, you might as well use what we did last time. So if you choose, this is along Z, right? If you choose C is 0, choose C is L. Yeah, then the solution is especially easy. Well, you can, the textbook use minus L/2 and L/2 here, make it symmetric. That is fine also, except that it's not as familiar. Last time we already did this problem with 0 to L. So in that case, the C part is especially easy. It's just whatever we call it, sign, because we want L part, we want when Z equals to R, then it becomes a sign L. L is an integer, so it's L. It's from 1 to infinity. And because it involves all the azimuthal angle, you can say use the case with M as integer, right? It's minus infinity to infinity, right? And so that will take care of the boundary on 0 and R. Z equals 0 and Z equals R. So that's fine, right? We need a coefficient, but we can figure out the coefficient a little later. And then the phi solution is this case, e that IM5 with all integer, right? And then the choice of J and N now depends on the row boundary, especially whether the problem involves the axis. The axis is rho equals 0. Right? If the problem involves the axis, then you know that all the y are singular at rho equals 0. The argument equals 0, all the Neumann functions are singular. Then you usually don't want singular solution unless you have very special situation. But if you don't want them to reset all the d to be 0, so you don't have the, you only have the j function, right? So that is what we have. So you have a coefficient like ALM, and Bessel function. Now it's n row. Now we need to figure out what n row is, right? Because we here we define your L. So this is your O L. When we define L, the whole L become L pi divided by R. That's the Bessel function. And what we did last time, the condition for the situation, the n actually defined as a squared equals to k squared, which is lambda, k squared. Let's just write it out first. K squared plus L squared. So k squared is our lambda, right? And L is our new. We define L. That go into here. So n, whatever that is. This. So L is from 1 to infinity, and now it's n is given by this. So n will be the square root of this one. Okay, but then we haven't actually chosen the boundary the eigenvalue yet. The eigenvalue is chosen such that it's satisfy the boundary condition at the surface of the cylinder. So this is at radius rho. This is rho. I mean, this is rho. This is R. The radius is R. The surface is at rho equals to R. Oh, is it R? So did I mix the I may have mixed the R and this is L. Sorry, this is L. This is L. This is R. This is L. I mix the parameter. That's okay. So at rho equals to R, then you need to satisfy the boundary conditions phi is 0, and which means you want the Bessel function to be 0 at on the surface. So you have J M n lambda n R equals to 0. Okay, so that is the boundary condition, and that implied n R what we call the equals to the 0 of the Bessel function m, and then usually we have you have infinite many zeros, so that could be what are the variable we and maybe we use L, we use J, maybe J. Right. J will be just count all the 0 of the Bessel function, right? Because you don't count the 0 at rho equals 0, because that obviously not at rho equals 0. That is all the Bessel functions. So you count integer Bessel function J0 is something like that. J sub 0. J1 is start from 0. J1 at this is the argument x. J1 at x is 0. So, okay. You just count wherever it goes to 0. You count this is x01, x02, and this is x1 at 1, and then where this is x12, and so on. And there will be infinitely many of them. Right? So you require that to be a 0, and n is given by that. So n squared, this is equals to, you require that n squared is x m j over r squared. Okay, so lambda equals to this minus that, so it depends on m, l, and j, right? So that would be the general solution. But generally, you have all these eigenvalues, and you can choose the smallest. I think the problem asks you to choose the lowest, smallest eigenvalue, which obviously in this case in this case is, wait, one more thing. I actually changed the sign of, actually this should be, because we all originally chose that this is L squared, but this problem is actually minus L squared. Actually, that should be I. That should be I, so that should be negative sign. Okay, so now lambda equals to L pi over L squared plus for all the possible L and M, and actually J, because we have infinite many of them. Okay, and so finally you need to sum over J also. Right, because, and the lowest one obviously is when L is, because L start from 1, so L, choose L equals to 1, and the smallest x in this case, if you just look at the graph, you see that the x01 is the x value that is the smallest. So it will be x01, and that is what your textbook calling alpha for the zero mole. So the lowest, for the smallest one, the minimum is equals to IL squared plus x01 L squared. Okay, so that is just the eigenvalue. Or obviously, once you figure out the eigenvalue, you can put it back to here or whatever here, and write down the form of the solution, find the eigenfunction. But this problem, that would depends on the lowest mole, it depends on the arbitrary amplitude. There's an arbitrary coefficient in front because it's a linear problem, but that is the general solution, because the problem doesn't give you the exact the condition, the fixed that constant, because you're just solving the eigenvalue and eigenfunction, right? And how large is it doesn't matter. Okay, so that is this example. It's okay.